Okay, this is a fun example. We're going to analyze what's known as a hydraulic jump. A hydraulic jump is where you get a sudden increase in the depth of a liquid stream when it flows over a horizontal surface. And you can sort of see a schematic of it over here on the right-hand side. You've got some flow coming in at a relatively high speed, u1, and the height there is h1, there's the free surface. And then you see there's kind of an abrupt change in height to a higher height, h2, and the velocity from conservation of mass will be slower, u2. So I try to illustrate that with a smaller vector there compared to there. So you get this kind of abrupt change in height, and you can see an actual picture of this. If you go to your sink, put a plate down, or in this case it's actually pouring onto the metal surface, you can see the hydraulic jump occurring. It's the water's coming in here, it goes out at kind of a high speed off to the sides here, and then you see the hydraulic jump, which is this kind of ring here, and then it goes to a slower speed and a thicker level of water outside of that. So go ahead and try it yourself. I'll wait. Go ahead and pause, go to the kitchen, get the plate, pour some water so you can take a look at it. I'll wait. Okay, great. Hopefully you've tried it. We'll go ahead and analyze this problem. When you think about it for a moment, first of all, you'll see that conservation of mass is going to come into play, right? That we have some height here, some height here. They're different. Velocities are different. You can tell pretty quickly you're going to have that conservation of mass is going to come into play here somehow. The other thing that might be less obvious is that linear momentum will come into play as well. And so how do I know that? Well, the reason I know that is because we have a change in the momentum of the fluid since the velocity is changing. So, high momentum here and then low momentum here because the velocity is going down here. So there's some force acting on the fluid that's causing this change in linear momentum. And I'll come back to what that force is in a moment. That's probably the hardest part of the problem, is figuring out what that force is. But we'll worry about that later. So let's first of all apply conservation of mass to a control volume. So we're going to have to choose what that control volume is. And since I want to relate the heights, h1 and h2, to one another, I probably want to choose a control volume that cuts across h1 here, cuts across h2 over here. I'll have it go across the bottom because there's no mass flow rate out through the bottom there or anything like that. And then I'll just have it follow the free surface. So that'll be the control volume I'll use. And let me put a coordinate system in here as well, just to have it. That's a fixed coordinate system. It's inertial, so I don't have to worry about acceleration effects or anything like that. And now let's apply conservation of mass to that control volume. So we'll write out conservation of mass. This is the procedure I prefer you take, where you write out the governing equation, and then we'll simplify it. So there's conservation of mass. The first term is the time rate of change of mass inside the control volume. Well, we're going to assume that this is a steady flow. If you actually run the little experiment in your kitchen sink, it's nominally steady. I mean, in a very short time scale, sure, you get fluctuations as it looks a little turbulent out here and such. But over a time scale on the order of seconds and such, it looks nominally steady. So we're going to say this is a steady flow. So that first term is 0. And again, if you set a term equal to 0, it's a good idea to indicate why. So it's equal to 0 because it's steady. If you find that you're uncomfortable writing, the word steady here, that means you don't really understand it that well. You need to study it a little bit more. Okay, so let that be a guide for your own self-study. So you want to make sure you're comfortable stating what your assumptions are. All right, let's go ahead and evaluate the mass flow rate term. That's this term. This is the mass flow rate out through the control surface. So we have mass flow rate coming in here at h1 and going out here at h2. Nothing is going out through the bottom because it's a solid boundary, and nothing's going out through the top because I'm just following the free surface. So we'll evaluate what's happening on the left side first. So we have the density. The relative velocity will just be the fluid velocity minus the control surface velocity. but the control surface is fixed, so it'll only be the fluid velocity. So that'll just be a u1 in the I hat direction, because it's in the positive x direction. And then that'll be dot product with the velocity, with the area there. So the area will be h1 times the distance in and out of the page. Let me just call that distance, I don't think we were told what it is, but I'll just call it b for the distance in and out of the page. So that'll be h times b, and that is actually in the minus I hat direction. Our outward pointing normal vector, n hat, remember it's pointing out of our control volume, at that area is pointing in the minus x direction, so that's where the minus I hat comes from. Oh, and I should put h1 because it's height h1 here, so that's our area. We weren't told anything about the velocity profile. We're just told that it's u1 coming in and u2 going out, so I'm going to assume everything is uniform. Okay, so I'm just going to, basically what I'm assuming is that the surface down here is frictionless. If it's frictionless, I don't have to worry about the no-slip boundary condition. And so it'll just make everything, I'm assuming it's all uniform coming in and the same sort of thing going out. And it's all uniform. Okay. And, if I was typing this up, I would say more clearly that it's frictionless on the surface, on the bottom surface here, just to add to my list of assumptions. Okay, so that's what's happening on the left-hand side. Let's do the right-hand side. So there, we still have the same density. I'm assuming that this is an incompressible flow. Water's reasonably assumed incompressible. The velocity there is u2 in the I hat direction. The area there will be h2 times the distance in and out of the page b, and that's in the positive I hat direction. Our outward pointing normal there points in the positive x direction. And then that's it. There's nothing going out through the top or the bottom, so that's all we have. So if you simplify this, going to work out the dot product and simplify it down, what you're going to get is h2 u2 is equal to h1 u1. Okay, so that's what we get from conservation of mass. By itself, it's not particularly useful. What we're trying to find ultimately here is the ratio of h2 over h1 in terms of only the upstream velocity and the upstream depth and g. We don't want it to include the u2. So we need to find some other equation to eliminate u2 or put it in terms of the other variables. So the other equation that we could consider using would be the linear momentum equation. We know that the linear momentum changes from the inlet to the outlet, so we might want to consider that. The linear momentum equation involves u2 and u1, so let's give that a try. That might give us the other equation we need to eliminate u2 from our equation. So we'll apply the linear momentum equation in the x direction, because that's my velocities are in the x direction. So we'll write down the equation and then simplify it. This first term is the time rate of change of x linear momentum in our control volume. The next term is our x linear momentum leaving our control volume through the control surface. Then we have our body force in the x direction and our surface forces in the x direction. Okay, let's start with the easy things first. So the first term is going to be 0 because, again, it's steady. Linear momentum isn't changing with time in our system, in our control volume. The next one will be the body forces in the x direction. That's 0 because we're showing that gravity is pointing downward, so we don't have to worry about that. Let's now evaluate the control surface, the linear momentum flux term. So we'll do the left-hand side first. The x velocity on the left-hand side is u1. That's in the positive x direction. This is this yellow highlighted term here. And then the mass flow rate term we just evaluated moments ago up here. So I'll just rewrite that. So this will be minus rho u1 h times b. So this is, I'll highlight this one in green. This term is this term. And it's the same thing as what we had right up here. All right, so that's our linear momentum flux on the left-hand side. You see that there's a minus here. The minus comes in because the mass flow rate is coming in. Okay, let's do what's going out on the right-hand side. So there, the x velocity going out is u2. Again, that's our yellow term here. It's this one. And then the mass flow rate term we worked out up here. So let me evaluate that. That'll just be the rho u2 h2 times b. And that's positive because the mass flow rate's going out. I'll highlight that as green because that's this mass flow rate term. It's the same thing that we evaluated previously. So that's it as far as the linear momentum flux terms. Those are pretty straightforward. It's pretty easy because we don't have to do the integral because we assumed everything was uniform. Now let's do the surface force term. Let's go back up to our picture here, and let me erase a few things just to make it a little cleaner. Okay, so let's take a look and see where we might have some surface forces occurring. Well, on the free surface, we're going to assume that the pressure is atmospheric pressure everywhere. So it'd be 0 gauge pressure, right? So there's no pressure force that we have to worry about on the top. You know, even with the change in elevation, there's no pressure force to worry about because we're dealing with gauge pressures. Viscous forces on the top would be 0 because it's just air out here, and the air will exert a negligible viscous force on the top surface. So we don't have to worry about viscous forces on the top. On the bottom, I said that we're assuming that it was all frictionless on the bottom as well. That's how we got the uniform velocity profiles. So I don't have to worry about viscous stresses on the bottom here. And in fact, I think I even said that down here. The shear stress between the liquid and the stream bed is 0. So I actually even said it here. Pressure forces on these faces. We do actually have pressure forces on these faces. And that pressure force will be a hydrostatic pressure force. So let me sketch it in here and then I'll talk about it in a moment. So we'll have our hydrostatic pressure force. It increases linearly with depth. And those pressure forces act inward. Now, you might ask yourself, it seems like a contradiction in terms. I'm saying hydrostatic, yet we have a flowing situation here. Well, the reason we can still use a hydrostatic pressure distribution is because the layers, the fluid is flowing in layers, right? It's nice and uniform, it's flowing in layers. If you think about a little piece of fluid here, in order for it to continue moving in layers, the pressure acting vertically here will be hydrostatic. We just have to, if you do a force balance vertically, you've got the weight of the piece of fluid that has to be balanced by the net pressure force acting on it. So even though this is flowing, since it's flowing in horizontal layers, you still have the hydrostatic pressure force distribution vertically. And so that's why I can get away with drawing the hydrostatic pressure force distribution here. If these streamlines were curved, let's say they had some curvature to them, then the pressure distribution actually wouldn't be hydrostatic. There would be some additional component that would take into account the acceleration because the curvature of the streamlines. But that's not the situation here. Everything's nice and horizontal. And so to support the weight of the piece of fluid in this gravity field, you would still get the hydrostatic pressure distribution. It's this hydrostatic pressure force difference that causes the change in the fluid's linear momentum. Remember, from Newton's second law, you have to have some force in order to change the linear momentum. And that net force is the difference in the hydrostatic pressure distributions. So we'll include those. So down here on the left-hand side, the resultant hydrostatic pressure force will be a 1/2 rho g h1. I should have put my h1 over there as well. h1 squared times b. And then on the right-hand side, that's pointing in the minus x direction because it's acting inward. A minus 1/2 rho g h2 squared b. So that's, again, the net pressure force on the left-hand side in the positive x direction. And then on the right-hand side, that's in the minus x direction. and that's the resultant pressure force there. Okay, so we actually have everything we need now to rearrange everything and put it all in terms of U1. Remember that what we're trying to find is H2 over H1 in terms of U1, H1, and G. So what we would do is simplify the linear momentum equation and then substitute in what we have for conservation of mass and then do some rearranging. So I'm not going to do all that. I'll just write it as simplify linear momentum equation and substitute conservation of mass, and then do some algebra. Okay, so I'm not going to go through all that. If you want to see how that's done, I actually have the written out solution for this problem available on the web, so you can look at the details. It's a little tedious and a little tricky, but it's just algebra. Okay, but in the end, what you'll get is H2 over H1 is a minus 1/2 plus square root of 1 over 4 plus 2 U1 squared over G H1. So that's what you'll get when you go through all of the algebra involved. It's kind of a complex looking relationship. Now, just from the, so we have this kind of math, okay, fine. Let's think about it though for a moment. H2 over H1, we know from the picture that for this hydraulic jump to occur, H2 has to be larger than H1, right? It's thicker here than over here. So we know that that has to be greater than 1. So let me add that on here as well. Now for that to be greater than 1, then we know this, we have to just satisfy this inequality, right? So we know that this inequality must be solved. So if I rearrange this to solve for U1, what we have for our upstream conditions, what kind of conditions we have to have for that in order to solve that inequality, what you'll get is that U1 squared over G H1 has to be greater than 1. Okay, so in order for this inequality to hold true, that must be true. Okay, and we need that to be true so that H2 over H1 is greater than 1. Okay, so this is actually part B of the problem. If you look up here in the problem statement, one inequality on the value of that parameter must hold for a hydraulic jump like this to occur, and that's what has to happen. This parameter actually is a well-known fluid mechanics dimensionless parameter called the Froude number. Froude number, kind of abbreviated FR, typically shows up as like U1 over the square root of G H1. You'll see that showing up frequently in fluid mechanics problems with free surface, like things with waves and free surfaces like what we have up here in this picture where the free surface height is changing. So anytime you have waves or free surface height changes, things like that, you have a Froude number that typically shows up. So here you can see that the Froude number squared has to be greater than 1. If the Froude number is less than 1, then you won't have a hydraulic jump. It just can't occur. We show that mathematically here that it's just not possible. You have to have a Froude number greater than 1 for that to occur. And we call a Froude number greater than 1 a supercritical flow. Froude number less than 1 is called a subcritical flow. So we need a supercritical flow to occur in this particular case. So I'll just make a note here. Froude number squared has to be greater than 1 for the hydraulic jump to occur. All right, so that's kind of a neat little example. Froude, let me just give you a little additional information. This kind of a system is often used as a poor man's supersonic wind tunnel. So these hydraulic jumps that occur here, and you see it in the picture over here, they're analogous in many ways to shock waves that occur in supersonic flows. So you know that if you have a high-speed aircraft going faster than the speed of sound, you can get a shock wave that'll form on it. The shock wave is really just a sudden change in the pressure and flow and density and temperature. The temperature, flow, pressure, density, all those things change abruptly across a shock wave in supersonic flows. You get a similar kind of behavior here for these supercritical water flows or free surface flows. You get an abrupt change in the height, in the speed, in the pressure, at the bottom at least, when you have this hydraulic jump. So the hydraulic jump is kind of like a shock wave. So sometimes people will make water tables where they get these hydraulic jumps to occur and use those sort of as an analogy to supersonic wind tunnels. Kind of a neat thing to do. All right, we'll go ahead and end the example there.